So, in the previous session we have introduced this very basic idea of process calculation, and that is the single stage extraction, right. But industrially we always go for multi-stage, because in single stage we do not acquire, or we cannot actually get that desired mass transfer, desired amount of mass transfer, desired amount of this solute removal from this carrier stream, right. So, that is why we have to go for multi-stage. Now, in extraction we can have the cross current extraction systems, where individually in each stages we are charging fresh solvents, okay, unlike counter current, which is not this cross current. This typical contacting pattern is not exactly possible in absorption or stripping or in distillation, but in extraction it is possible, because we have to add the third component, which is the solvent, and we can do it. This addition we can actually facilitate in each and every stage. So, let us discuss about the cross current extraction. So, the schematic, you see how we can describe that. This is the stage 1, stage 2, then we will have an intermediate generalized state I, and last stage, that is N. Okay. So, in the first unit we are giving the feed flow rate is F, and the mass fraction of C in the feed is ZF, right, just like the previous. Now, in the first stage we are adding solvent at a rate of S1 and its composition is YS. So, taking out the extract, which has got a flow rate T1, its composition of Y1, and feeding the raffinate as a feed to the next stage. So, it is R1 comma X1. So, the raffinate, see, solvent, what is the specific characteristics? That solvent is added in each stage individually. There is the first point. The second point will be the raffinate generated in a stage is being fed to the next stage or being fed to the next stage, right. So, just like the raffinate generated in stage 1 is, we are feeding it to the stage 2, right. So, this is the source of the solute here, and we will further carry on the separation process subsequently upon adding solvent in each of the stages. So, here we get E2 Y2. So, from the stage 2 we are generating the raffinate R2X2. Here definitely it is Ri minus 1, Xi minus 1, we deliver the solvent at rate Si, composition remains same Ys, because the solvent is being delivered from a common header. So, its composition remains same, we can change the feed rate to that specific unit, feed rate of the solvent. So, it is Ei, Yi, so here it is Ri Xi, so Rn minus 1, Xn minus 1, here we give Sn, Ys, the same, we are getting En, Yn, and finally the raffinate Rn Xn, right. So this is the final raffinate, which is actually the spent, right? So we write it as final raffinate. So you see that overall material balance in stage I, how we can write that? Ri minus 1 is the inflow, Si is the inflow, Ei and Ri are the outflows. So Ri minus 1 plus Si, definitely it will be producing a mixture, and that's equal to Ri plus Ei, just like the single stage extraction process. And component material balance in stage I is Ri minus 1 Xi minus 1 plus Si Ys is equal to Mi Xmi equal to Ri Xi plus Ei Yi, right? For I equal to 1 to n, for I equal to 1 or rather R0, this is R1, so this must be R0. So R0 is F and X0 is ZF, right? Now you see, for individual stages, if I start solving it from here, so these two values, they are known, right? Solvent, fluoride, solvent composition are also known. So we have to solve for, according to this equation, solve for 6 variables, right? Just like the single stage extraction, that is Mi, Xmi, Ei, Ri, Yi, Xi. But we have 4 equations. So degrees of freedom is 2. So we have to get recursively the 2 variables of this out of this list from somewhere else, and that we will use the triangular diagram. Yi and Xi are to be evaluated from triangular diagram. So what we will do here? So we draw this bimodal solubility curve, and let's say this is the plate point and these are the tie lines which we have used, and this equilibrium, respective equilibrium data we have used in drawing this solubility curve. So this is C, this is A, this is B, right? So you locate that point S, right? Solvent Ys, okay? And we also locate the feed F, which is alternatively R0 from its composition ZF. Next, the composition of the mixture generated here. So here we are generating a mixture of composition XM1. So XM1 must be lying on the line joining F and S. So you draw this line and locate the point M1, right? Now using the idea of conjugate line as we have discussed in the previous session, draw a tie line through this point M1, determine the point E1 and R1, right. So, steps: knowing F, ZF and S1, solve for M and XM or M1 and XM1. Locate point M1 on the line Fs. You can use this lever arm rule, or you can go for analytical calculation, whatever you wish, right. So, third is draw a tie line through M1 and locate E1 and R1, that is, get Y1 and X1, right. Solve for E1 and R1, the fluorides. Now, once you have located the point R1, see, the R1 is the feed to the next unit. So, you have located point R1. Now, the composition of the mixture, that is XM2, must be lying on the joining line of R1 and this S. So, if I draw a line here, we can locate point M2, repeat the same process. So, this is R2, again go on repeating the same unless and until you reach RNP, right. RNP, respective composition is XNP, that is less than the desired composition XN, right. So, join R1 and S, solve for point M1 or M2 and repeat the same process. Unless we get XNP that is less than XN, given XN is given because in design, see, design means we have to determine the number of stages, okay. So, let us say in a cross current problem, cross current extraction problem is given to you, this you know and this also you know, this is known, right. Now, Sn, Si, S2, S1, how much feed you are giving in individual units, that is mostly under optimal situation these individual fluorides are constants, right. So, same. So, you go on repeating that and unless you get a point RNP where it is less than the target raffinate concentration. So, there we stop and finally, RNP, NP will be my number of stages required. So, this is about the cross current extraction system, but the same idea we can extend if the system is immiscible, the carrier and the this solvent, they are immiscible in the cross current extraction problem. So, let us discuss this immiscible carrier and solvent in cross current extraction or liquid extraction. So, here we use solute free bases. So X is what? X represents the raffinate phase composition. It's the amount of C in amount of A, and Y, it is the amount of C amount of B, because we have two components per phases. In the extract it will be B and C only, in the raffinate it is A and C only, because A and B are immiscible. So under this situation you see how to go for this calculation of the number of stages. It is much easier compared to the previous one, right? Here the simple capital Y versus capital X space and the calculation in the respective space is sufficient. So if I again draw this stage I, here I have A, because A remains same, right? A is what? Flow rate of carrier, only carrier. Now the carrier amount, it's not changing from one stage to another stage, because carrier and the solvent are immiscible, and in that stage we are giving Bi, right? That's a flow rate of pure solvent, and its composition capital Ys, right? So Ys represents what? Kg of C per kg of B, right? Why? Because the solvent is regenerated, there may be some amount of C only present in this solvent which we are charging in that system. So here we will get Bi, Yi, and just very similar, it is A, Xi. So if I write the balance, here the balance is much easier. A into, here it is Xi minus 1, A into Xi minus 1 minus Xi is equal to Bi into Yi minus Ys. So Yi minus Ys divided by Xi minus 1 is equal to minus A divided by Bi. So that's the equation of operating line. Right? So how to determine the number of stages? Here, see, Y and X, they are in equilibrium. This Yi and Xi, they are in equilibrium. So how to determine the number of stages? We will draw the equilibrium data in the capital Y, capital X space, and let's say this is the equilibrium curve. Right. And we also mark the point Ys and draw a dotted horizontal line. Now from the first point will be what? X0, which corresponds to Zf. X0, which is equal to Zf by 1 minus Zf, right? Now from there I will draw a straight line with a slope of minus A by B1. So from this equation it's obvious that I will get X1 and I will get Y1, and from here again I will draw another straight line, slope minus A by B2, so I will get Y2, I will get X2. Here again another straight line with slope minus A by B3, so this is Y3, this is X3. So definitely there will be some point which is Xn, that is a desired concentration. So once it crosses, we have the cross here XNP, right. So, here we should stop and NP will be my required number of stages for this desired cross current operation. So, cross current definitely it gives you flexibility because you can go on changing the amount of solvent, right, wherever required, but that is not definitely its feasible contacting pattern for large scale extraction, right, which is where we have to go for counter current mode. So, in counter current, let us discuss what will happen and what will be the change in this process calculation for the counter current liquid-liquid extraction. So, for counter current liquid-liquid extraction, দেখে নেবেন এটা কেটে দেবেন। So, for counter current liquid-liquid extraction, see, will mark the stages, equilibrium stages from the feed side. Here we are giving the feed F ZF, and there will be a general stage I, and finally N, and we charge the solvent from the opposite side S YS, right. So, you see that extract from stage I will be used as a solvent in stage I minus 1, just like here. Here we are generating raffinate, so R2 X2, this is the extract from stage 3 E3 composition Y3. So, this is being used as a solvent in stage 2, generating the extract E1 at a fluoride E1 composition Y1, which is being used in stage 1 as solvent and generating the final extract. Sorry, this is E2 Y2 and this will be E1 Y1. Here the raffinate from the stage 1 is treated as a feed in stage 2, right. So, here we have raffinate Ri minus 1, Xi minus 1, raffinate Ri, Xi, here Ei plus 1, Yi plus 1, here Ei comma Yi. So, here it will be Rn minus 1, Xn minus 1, and final raffinate Rn Xn, and we have En Yn, right. So, this is fresh solvent, final raffinate, then it is final extract, and this is the feed. So, if we go for an overall material balance and component balance over this cascade, let us say this one is the cascade, say it is the envelope 1, right. So, for envelope 1, we have this F1 plus S is equal to some hypothetical mixture fluoride, considering it to be single stage, which actually has got no meaning, right, Rn plus E1. And similarly, F1 into ZF plus S into YS, M XM, Rn Xn plus E1 Y1. Right. So, you see that we can write this in a different form, like F1 minus E1 is equal to Rn minus S, and let us call this difference as delta. Right, we are defining this as delta. And similarly, from this component balance, F1 or F, or rather F ZF, E1 Y1, Rn Xn, S Ys, let us call it delta into X delta. Right. So, what does it mean? It means that we have 2 points, E1 minus F, E1 and F. F, E1 and delta here, Rn S delta here, right. So, Rn, just let me check, E1 plus delta, or alternatively we can write this is minus, this is plus, and this is minus, this is plus, and this is minus plus, and this is minus plus. Okay. Why I am changing it? Because according to stoichiometry, see, if I am mixing F1 and delta, solution marked by the point delta in this phase space, I should get E1. So, what I am getting here? E1 is equal to F1 plus delta, and FZF plus delta X delta is equal to E1 Y1. So, I will get this, and similarly is true for if I mix a solution Rn at marked by the point Rn composition and marked by the point delta, I must get a solution which is marked by point S, right. And that is why I have changed the minus sign to plus, otherwise it was bit different, it was just like F is here, E1 is here. So, it is not the case. So, alternatively we can say that what is the significance of these delta points? Now, we have a solution at E1, right, and from there if I abstract a solution of amount F and composition ZF, I will get a solution of amount delta and composition X delta, and same is true for S. From the solution S of amount S and composition Ys, if I abstract a solution of amount Rn and composition Xn, I will again get the same solution marked by the delta point with an amount delta. So, this is the basic idea, right, and this idea we will explore to determine the number of stages. Now, what we do, so we now will go for another envelope, right, envelope 2. So, for envelope 2, we have this, you see, Ri minus 1 plus S is equal to Ri minus 1 plus S is equal to Rn plus Ei, and Ri minus 1 Xi minus 1 plus S into S into Ys is equal to Rn into Xn plus Ei into Yi. And upon changing it, what we will get? We will get this Rn minus or S minus Rn, S minus Rn is equal to Ei minus Ri minus 1, and by definition S minus Rn is delta, right? And similarly Sys minus Rnxn is equal to Ei minus Ri minus 1 Xi minus 1, and that will be x into x delta. So we can think of another point which is Ri minus 1, here it will be Ei, and this if we connect and extend, right, they must meet at point delta, and that gives you the idea that how to calculate the number of stages in case of countercurrent liquid-liquid extraction. See what we are doing. So this is the solubility curve. Here I have located the point F, we have located point S, we have located point RNP, and we have located point E1, right? Because this we can obtain from the material balance. As my final raffinate composition will be given, see, this will be given, Sys will be given, FZF will be given, right, and final extract that will also be given. So from there, by using the overall material balance, we can locate F, we can locate RNP, we can locate E1, we can locate S, we can locate. So with that, if I now join just like here F and E1 and extend, and here I join RNP and S and extend, I will get the delta point. Right. So that is the overall envelope. This angle gives you overall envelope of this entire system, right? All this data will be here. All this E1, E2, E3, E4, R1, R2, R4, whatever it is will be inside. So what we have to do? From E1 we have to draw a tie line. So definitely it must be R1. Now R1, if I join, see this I minus 1, this I is 2, right? So that gives you R1. So R1, if I join to delta, it must intersect the binaural solubility curve's right hand side, that is the extract term, at this point E2. Okay? So if I join it, sorry, I will get the point E2. And again from E2 I will draw a tie line, and this must be R2. Again R2 and delta will be joined and it will intersect here at E3. So in this way we will continue, this is E3 and again the tie line, and we will continue unless we will get a tie line going below this point RNP, so or Rn rather, Rn, because we haven't used RNP, it is Rn, right? And let us say this is RNP where XNP is lower than Xn. So NP is the number of stages necessary to achieve this specific requirement. Okay. Now there is an alternative technique, because you see that if my number of stages we find 30, 40, something like that, so it's practically impossible to go for graphical calculation, drawing individual stages and all, right? So there we will use an alternative technique. What is that? See. So keep in mind that F E1 delta is on the same line, RNP S delta on the same line, Ri minus 1 Ei and delta, they are also on the same line, and that is the clue to solve for this number of stages. So, what we do here? We have this triangular diagram. Next, we will locate F, Rnb or Rn, right, S and point E1. Draw this or locate the delta point. Right, and also here side by you draw this x and y, the 45-degree line, and from the tie lines like this, and this is the plate point. So, draw the equilibrium line. Right. Now, you see at any section, just like here, what are the streams? Ri minus 1, composition Xi minus 1, and here it is Ei with composition Yi. So, we have seen that from delta point, if I just draw any line, it will intersect the extract arm at Ei and raffinate arm at Ri minus 1. So, if I draw some arbitrary lines from the delta points, like this, some arbitrary lines, they will be intersecting here at probable Ei and Ri minus 1, which are points on the operating line, because the operating line means something which will relate the property of two countercurrent streams. So, this will project this represents y, this represents yi, right, and this represents xi minus 1. So, here and here, so it will be operating line here, right. So, the operating line we will draw like this, projecting all this, and from there I will locate the 2 points. These are operating lines, right. Locate the 2 points, first one which is ZF and Y1, and another point which is these XN and YS, and go for the staircase construction between these two, right. So, here definitely it is manual drawing. So, between these two you have to go for staircase construction, because we have the operating line and equilibrium line, and from there we can simply calculate that what will be my number of stages. What we were doing by tedious graphical construction, we can simplify it, but though the initial construction will be much more, we have to construct this y versus x space. So, that is about the countercurrent extraction, but here lies a problem. Problem is the solvent flow rate will not be provided. So, we have to, very similar to that previous all these mass exchangers, we have to calculate the minimum solvent flow rate. Okay. So, for minimum solvent flow rate, I am not going into the detail for these immiscible systems. Just I will describe the process, you can understand. This is the construction simply. See, determination of minimum solvent flow rate, that is SM. So, how to determine the minimum solvent flow rate? See, again draw the triangular diagram, the binodal solubility curve. You can locate the point F. And let us say the plate point is here. The tie lines are inclined like this. Right. Now locate the point Rn. You can also locate the point S. Right. Now what we have to do? We were drawing operating lines. See, these were the tie lines, and operating lines were what? Operating lines, see, tie lines. We have one like this and this, and operating lines are the joining lines of Ri minus 1 and Ei. So, if these operating lines are also like this, okay, because there will be some delta points, and if I know the solvent flow rate, we can locate the delta point and we can draw the operating lines. Now, when operating lines and tie lines merge, then it corresponds to minimum solvent flow rate, right, which is alternatively equal to the infinite tower height. So, what we have to do? We will join and extend this RNP and point S like this, right, and below this point F, whatever tie lines we have to extend all the tie lines on these joining lines, or such that it intersects on the joining line of RNP and S. What is that? Like this. Etc. etc. So, they intersect at here, here, here and here. Okay. So, what is the theory? The theory states that for Sm, the respective delta point will be closest to point S, closest among all intersections between Rn, S and tie lines. If delta point or tie lines are sloped right or sloped along right hand side, which is the case here, right. So, this point, which is the closest, corresponds to delta m. So, once I know this point, so definitely Sm by lever arm rule by Rnp is equal to Rn, not Rnp, Rn into delta m by S into delta m. From the lever arm rule, determine Sm from lever arm rule and material balance. over envelope 1, right. And alternatively, if the tie lines are inclined towards left, so here the tie lines are sloped along right hand side, here the tie lines are sloped along right hand side. So, if it is sloped along left hand side, it will be the farthest one, right. So, for SM the respective delta point will be closest among the intersections, right, between RNS and tie lines if the tie lines are sloped along right hand side. Alternatively, it is the farthest, or it is the most distant intersection if the tie lines are sloped towards left. Right. So, if the delta point or if the tie lines are inclined like this, so it will intersect the R and P's S on this side, and in that case it will be the farthest one. I am not going into the detail of the theory because it is not required that much, but more importantly we will discuss now what will happen here if I have an immiscible carrier and the solute solvent combination. So, counter current LLX for immiscible carrier and solvent. So, first definitely use solute free basis, right, that is capital X and capital Y, the notations we have introduced just previously. It is the kg of C per kg of B, that is Y, and kg of C per kg of A, that is X. So, if I consider a general stage I, so here we have A and xi minus 1, and here it is B yi plus 1. Going out is A xi, and here it is B yi. So, simple balance will yield that A within bracket xi minus 1 minus xi equal to B yi minus yi plus 1, right. So, xi minus 1, sorry, yi by yi plus 1 divided by, this is increasing, this is decreasing. So, by xi minus 1 minus xi, it is equal to A by B, right, and that is the equation of operating line. Why? Because operating line means here just xi minus 1, see here xi minus 1 is related to yi and xi is related to yi plus 1, right. The 2 points on the operating lines. So, what we have to do in order to calculate the minimum solvent flow rate or the number of stages? First, we go for generating the equilibrium curve in this y versus x space, capital Y versus capital X space. So, it is equilibrium curve, right. Next, we locate, this is xn, this is ys, and we have this as the x0, which is zf. ZF divided by 1 minus ZF because it is immiscible. Okay? Now, the slope must be A by B, and for the minimum solvent flow rate, the operating and equilibrium line must touch each other. So, this is just like the previous cross current extraction, that is the limiting operating line. Slope is A by B minimum, solve for B minimum, and B will be 1.25 to 1.5 times of B minimum. Right. So, you have determined the minimum solvent flow rate and therefrom the operating solvent flow rate. So, we will draw this operating line, and here we get Y1, and between these two we will draw a staircase to determine the number of stages, right. So, from staircase construction, determine the number of stages. So, that is about the cross current liquid extraction system, counter current liquid extraction system for immiscible carrier and the solvent. So, that is all about the process calculation of cross current LLX, and overall process calculation. We have covered the single stage, then this cross current and counter current. In the next session, we are going to discuss about the different extraction equipments and the respective hydrodynamics. Okay, thank you.